Chapter 1, Part 3, Bonding, the Octet Rule, and Lewis Structures. Let's start with the nature of chemical bonds and the octet rule. So there are two main types of chemical bonds. You have the ionic bond, which is not truly a bond, it's more of an attraction. These are formed by the transfer of one or more electrons from one atom to another to create ions. These are redox reactions. One species is being reduced, the other is being oxidized. This creates an attractive force between the two oppositely charged ions. We also have covalent bonds. This is the main type of bond that we talk about in organic chemistry. This is when electrons are actually shared between atoms. All bonding uses valence electrons. So if something is reduced and oxidized, the species that is reduced is gaining electrons. The species that is being oxidized is losing valence electrons. A covalent bond is formed by the sharing of valence electrons. All elements except for hydrogen and helium want to have 8 valence electrons, and this is where the name octet rule comes from. There's a video that's linked here, not on this video, but if you open up the PowerPoint, and I am kind of sorry that I'm sharing it. Atoms will make bonds or undergo redox reactions in order to achieve the octet rule. So all elements want to have those 8 electrons, except for our exceptions. Our next topic is electronegativity. Electronegativity is the measure of the ability of an atom to attract electrons. This property, if you're looking at the periodic table, increases from left to right and up the periodic table. If you need a refresher on this, you should look up periodic trends. You can do this in your general chemistry textbook or just Google it and find a video on YouTube. But one of the important trends on the periodic table is electronegativity. Atoms that have higher electronegativity, such as nonmetals, are more likely to gain electrons through covalent bonding or through reduction, through the process of ionization. Remember that reduction is the gain of electrons, and so if you have higher electronegativity, you're more likely to be reduced than oxidized. So for example, chlorine is a nonmetal. In a reaction with an oxidizing agent, chlorine is likely to be reduced into 2 chloride ions because this allows for the gain of electrons. You might recall from Gen Chem 1 that if you were actually counting up how many electrons each species here, or each atom of chlorine actually owns, they have to divide this bond. So each chlorine atom owns 7 electrons. They are sharing the 2 in the covalent bond, which fulfills the octet rule. But if you were to reduce this molecule, you could give each of them their own octet without having to share. And since chlorine is electronegative, it actually really likes that idea. Another example is through covalent bonding. So oxygen is a highly electronegative atom, which means that it likes to form bonds with other atoms so that it can have a full octet. And when it does that, it actually takes the covalent bond, which has a sharing of electrons, and it makes that sharing unequal. This is called a polar covalent bond. So oxygen being so electronegative is going to end up having a partial negative charge, while the hydrogens are going to have partial positive charges. Remember that these are not true charges. The oxygen does not have a formal charge of -1, and the hydrogens do not have formal charges of +1. What we are saying is that if you were to draw the electron cloud of this molecule, which is being formed through covalent bonds, the electron density would largely live on oxygen, and the hydrogens would have very little electron density on them. Atoms that have lower electronegativity, such as our metals, especially the group 1 and 2 metals, are more likely to lose electrons through oxidation. So we're going to look at this reaction again, but with an actual redox reaction being apparent. So if you take sodium metal and react it with chlorine gas, you're going to get a redox reaction where chlorine is reduced to 2 chloride ions, and sodium is oxidized to 2 sodium plus ions. The sodium has lost an electron, which is oxidation, and the chlorines have each gained 1 electron, which is reduction. So if we're looking at our periodic table of the elements, I just want to remind you of this periodic trend again. So cesium is the least electronegative element on the periodic table, and fluorine is our most electronegative. So if you are trying to determine relative electronegativity, the atoms which are closer to fluorine are going to have higher electronegativity. So based on this trend, we know that oxygen is more electronegative than nitrogen. This does get a little tricky when you think about hydrogen. Electronegativity-wise, hydrogen belongs like more over here, closer to carbon. And the noble gases are, the noble gases are not electronegative at all. So let's look at another definition. We've already talked about elements and compounds. Elements are made up of only one type of element, and that can include molecules of diatomic elements. We also have compounds, which are made up of 2 or more different elements. The definition of a molecule is that it's composed of atoms joined by covalent bonds. So earlier we saw nitrogen gas. This is a molecule because it has 2 atoms that are joined by covalent bonds. Water is also a molecule because it has 3 atoms that are joined by covalent bonds. Now let's talk about the term compound again real fast. Nitrogen is not a compound because it only has 1 element present. Water is both a compound and a molecule because it has 2 different elements present and they are joined by covalent bonds. So not all molecules are compounds. Compounds can be ionic or they can be molecular. So something like sodium chloride can be considered a compound, but it is not molecular because there are no covalent bonds present. And again, compounds can also be molecular, such as water. You can also have compounds that are both molecular and ionic. Not to get a little crazy, I don't want to get too crazy, but we have something like ammonium chloride. Ammonium is nitrogen with 4 hydrogens on it. It has a positive charge, and if it's ammonium chloride, it has a counter ion of chloride. This is ionic because each species is charged, but the one of the ions is actually molecular, so we got a little complicated here. But the point of this is that different things can be categorized with these definitions, and sometimes the definitions overlap and sometimes they do not. So let's talk about how molecules are represented. We're going to talk about ethyl alcohol or ethanol, which is our drinking alcohol, not something that you usually think of as organic necessarily, but it has 2 carbons, so it is an organic molecule. We're going to look at a couple different ways to represent ethanol. We have the molecular formula, the condensed structural formula, and the molecular structure, which can also be called the Lewis structure or the structural formula. So the molecular formula of ethanol is C2H6O. So there are 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen. Now, what the molecular formula does not tell us is how are these atoms actually arranged. That's where the condensed structural formula comes in. This is a way of telling us that 3 of the hydrogens are attached to this 1 oxygen, or carbon. The 2 carbon atoms are actually going to be attached, and these 2 hydrogens will be on this carbon atom. The carbon and the oxygen will be attached, and the hydrogen will be on the oxygen. So if you were drawing out the Lewis structure, this one is a lot more helpful than this one. You would still eventually probably get to the right structure, but this molecular formula can actually be interpreted in different ways, which is something we'll talk about in another video. So condensed structural formulas are a little more specific. Now, the most helpful is the molecular structure, or the Lewis structure. This actually shows us the covalent bonds between the carbon atoms and the oxygen atom, showing us kind of the main framework of the molecule. And then the hydrogens are kind of like little ornaments on here. They are just coming off the main framework of the molecule. But this tells us exactly what the structure of ethanol is, whereas this can actually be interpreted in at least one other way that I can think of. Only one other way, really. So let's talk about how we come up with Lewis structures or Lewis dot structures. There are a couple different steps here that you can follow. So step 1 is to add up all of the valence electrons in the compound. These are the electrons that you can use for bonding, and so it tells you how many bonds you can actually make. The next step is to determine the central atom and then take the other atoms and arrange it around it. Now, since we're in organic chemistry, when you see carbon, carbon is your central atom. And if you have multiple carbons, a good first step is usually to take all those carbons and link them together. That's not always the final thing, but usually the carbons are connected. The next step is to draw single bonds between all of the atoms, and then give each atom an octet of valence electrons. You can do this in two ways. You can either do this with lone pairs, or through adding multiple bonds. The number of valence electrons that you have will kind of help point you in the right direction. And then count all your electrons and make sure it adds up to the number of electrons that you found in step 1. So let's do some practice problems together. In each of these, I'm going to indicate a time for you to pause where you can try it yourself. We're going to do the first one completely together, and then hopefully for the other 3 problems, you'll pause the video and try to draw it out yourself, because you are going to be expected to draw Lewis structures pretty regularly through organic chemistry. It's mostly structure drawing once you get past the first couple chapters. So this is a very important skill, probably the most important thing in this chapter. So our first molecule is C3H8. So let's think about our rules. The first thing that we're supposed to do is to count up all of the valence electrons. So hopefully we recall, you can look at the periodic table and come up with your valence electrons. Carbon is in the 4th column of the periodic table if you ignore the D block. And so carbon has 4 valence electrons. We have 3 carbon atoms. So 3 carbons times 4 valence electrons gives us 12 valence electrons from carbon. Hydrogen is in the 1st column of the periodic table, and we have 8 hydrogens. So times 1 valence electron per hydrogen, that gives us 8. That adds up to 20 valence electrons. Now, the other thing that you have to remember about covalent bonds is that each covalent bond is made up of 2 electrons. So if we have 20 valence electrons, that means that we can make up to 10 bonds. So let's take our carbon atoms and string them up, because that's carbon is going to be our central atom. This is organic chemistry, and I told you that a good shortcut is to put all of the carbons in a row. And I'm drawing them in a zigzag way because that's how you're going to draw most organic compounds. This will make a lot of sense when we get to line bond structures. So those are our 3 carbon atoms. And then we have 8 hydrogens. So let's just go ahead and arrange all the other atoms around the carbons using single covalent bonds, and let's see where that gets us. So carbon can only have 4 bonds total because that gives it a full octet. Right, so there are 8 electrons that carbon is currently accessing or sharing. This carbon can have 2 more hydrogens on it. That gives it an octet. So I'm going to give it a different color real fast. So that's 8 electrons around this carbon. And then our last carbon can have 3 hydrogens, and that gives it a full octet as well. Okay, so we've made it through most of our steps, right? We counted up our valence electrons, we found our central atoms, and then we arranged everything else around it, connected them all using single bonds. So let's see how many electrons we've used so far and see if we have any more work to do. So we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's all of our valence electrons, and that happens to be 10 single bonds. So this molecule is done. This is the Lewis structure for propane. So our next molecule, CH2O, I'm going to give you a second to pause for yourself. Okay, welcome back. We're going to work through this one together. Hopefully you paused the video and drew it out for yourself and you now have something to compare to. So we have 1 carbon, and we know that each carbon comes with 4 valence electrons. We have 2 hydrogens. Each hydrogen comes with 1 valence electron. And then we have 1 oxygen. Each oxygen comes with 6 valence electrons. That looks like the number 10. I'm so sorry. 1 oxygen. So if we add this up, that gives us 12 total valence electrons. So the next step is to identify our central atom. Our central atom is carbon. And then we have to arrange the other atoms around it. So we have oxygen and we have 3 hydrogens, or 2 hydrogens. Sorry, I was counting the number of things. So this is CH2O. The next step is to connect everything with a single bond. Now let's count up how many electrons we've used and see if we've used everything. We've used 2, 4, 6 electrons. And the next thing that we have to consider is, does everything have an octet? Except for hydrogen. Hydrogen doesn't need one. So currently, carbon does not have an octet. So there are a couple options. We can either put a lone pair on carbon and then put the other lone pairs on oxygen. If we add all this up, that gets a little messy because oxygen doesn't have a full octet now. Our other option is to put a double bond between carbon and oxygen. And this is going to be much better because now both carbon and oxygen have a full octet. So let's see what we've used so far. We have 2, 4, 6, 8, 10, 12 electrons. So this is the correct structure. And in fact, this molecule is formaldehyde, which may be a word you've heard before, usually in reference to the mortuary sciences. Okay, next one. Go ahead and pause and take a second for yourself. Okay, welcome back. We have 1 carbon atom, and that's going to come with 4 valence electrons. We have 5 hydrogen atoms. That's going to come with 1 valence electron each, so that gives us 5. And then we have 1 nitrogen atom, which is going to come with 5 valence electrons of its own. This gives us a total of 14 valence electrons to use. So our central atom is carbon, and then we have nitrogen and 5 hydrogens. So our usual process here is either to attach all of the carbons if possible, but there's only 1 carbon. The next idea is to arrange everything around the carbon, but we have 5 hydrogens and 1 nitrogen. That would be 6 things around carbon, which would give it way more than an octet, and carbon cannot handle that. So we have to get a little more creative. Let's put a bond between carbon and nitrogen, and now let's try to arrange everything around these guys. So we can put 3 hydrogens around carbon. Let's go ahead and connect those as single bonds. And that leaves us with 2 hydrogens for nitrogen. So nitrogen does not yet have a full octet. Let's see how many electrons we've used. We've used 2, 4, 6, 8, 10, 12. We have one more pair of electrons that we can use. Let's go ahead and put a lone pair on nitrogen. So now nitrogen has a full octet, carbon has a full octet, and the hydrogens don't care. So this is a good Lewis structure. This is the structure of methylamine, which, if you were a fan of Breaking Bad, is probably a word that you've heard quite a lot. Okay, let's do another example. CH2O2. Go ahead and pause for yourself. Okay, welcome back. Let's go ahead and add up our valence electrons. We have 1 carbon, 4 valence electrons from each carbon atom. That gives us a total of 4 from carbon. We have 2 hydrogens times 1 valence electron each, gives us 2. And we have 2 oxygens. We're going to draw those far apart this time so it doesn't look like 20. 2 oxygen atoms times 6 valence electrons each gives us 12. So if we add all this up, we get 18 valence electrons. So let's go ahead and start off with our central atom, which we know is going to be carbon. That's why organic chemistry is so great, is because you always know that everything's going to be centered around carbon. So Lewis structures with organic compounds tend to be pretty straightforward. The next thing that we have to do is arrange everything else around carbon. Okay, so that gives a full octet to carbon. Let's give a full octet to everything. Okay, now how many electrons does this take? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, so that's a problem. This cannot be our structure. This is the only way to give all of these atoms that need an octet, but that's going to use too many electrons. So we're going to have to use some double bonds somewhere. So let's try again. Carbon as a central atom. Let's put 1 oxygen on there, 1 hydrogen. Now we have to get creative. Carbon cannot make multiple bonds between hydrogens, right? That's just not going to work. So we're going to have to make a multiple bond to an oxygen. Let's make that look less crazy. Now the next thing that we have to think of is if we attach a hydrogen here, we still have to put the oxygen somewhere, the other oxygen. And hydrogen cannot make 2 bonds, so this is not going to be the way that we can do this. We're going to have to put oxygen here and attach hydrogen to it. So this gives us a rough outline. Let's go ahead and finish off using up our electrons, because not everything has an octet yet. Carbon is happy. It has an octet. But this oxygen only has 4 electrons around it, and so does this one. So they're only halfway there. The only way that we can fix this, since carbon is already happy, we can't add more multiple bonds, we're going to have to put lone pairs on the oxygens. Now let's see how many electrons this uses up. 2, 4, 6, 8, 10, 12, 14, 16, 18. So this is the correct structure for this molecular formula. And this molecule is formic acid, which can also be called methanoic acid. Now you might notice that you've seen this prefix already, form. Form is a common way of referencing a compound that has one carbon. Meth is the official way of saying that something has only one carbon. And we'll get to naming in chapter 4. Form, this prefix, actually comes from the scientific word for ants, which I do not know off the top of my head. I should have looked this up before I started this video. Because formic acid is actually found in ant venom. So when you're bitten by an ant and it burns, it's because they've just injected you with formic acid.